Hi, my name is Elena Gribelyuk, and in this talk I'll tell you about our recent work, A Strong Separation for Adversarially Robust L0 Estimation for Linear Sketches. This is a joint work with Honghao Lin, David Woodruff, Huacheng Yu, and Samson Zhou. Let's begin by defining the standard streaming model. Here we're given an input stream pi of elements which arrive one at a time. This stream is worst case, and it's fixed in advance of the runtime. At the very end of the stream, after processing it, the algorithm should output an approximation of some function, which was chosen in advance and known to the algorithm. Importantly, the goal is to design algorithms that use space that's sublinear in the size of the input stream. Today, the specific streaming problem we'll focus on is the distinct elements problem. As before, we're given an input stream of elements from some universe, 1 through n, and we look at the frequency vector of elements arriving in the stream. Here, fi is the number of times I appears. We'll consider the problem of estimating the f0 of the stream, where f0 is defined in this formula here. It's just the number of non-zero coordinates of the frequency vector. This exactly corresponds to the number of distinct elements in the stream. Since it's known that we cannot hope to achieve sublinear space deterministically, our goal is to design randomized algorithms that output a 1 plus epsilon approximation to the f0 with constant probability. Let's look at a quick example. If the stream is insertion only, we might get the following stream and a corresponding frequency vector x. Here, the algorithm should report that there are 4 distinct elements since there are 4 non-zero entries in the frequency vector. This problem has been studied very extensively over the last 20 to 30 years. Many works focused on achieving an optimal space for computing a 1 plus epsilon approximation, and this line of work culminated in this final bullet point here, which is optimal. In the case that we're fine with just an additive epsilon times n approximation, we can actually do something much easier. We can just sample 1 over epsilon squared elements uniformly at random. In this work, we'll study a slightly different model of streaming, which is called the adversarially robust streaming model. In this case, we still have a stream of elements which arrive one at a time, but now the stream is selected by an adaptive adversary. What does adaptive adversary mean? At each time in the stream, the adversary presents a query or update, and the algorithm needs to update its internal state and return a current estimate for the function on the stream seen so far. So the goal is still to design algorithms that are sublinear in the size of the input stream, but now the algorithm needs to satisfy a stronger correctness requirement that it is correct even in the setting when the adversary chooses the stream adaptively. For example, the adversary might select updates as we see here, and at each time point, the algorithm needs to respond with a number of distinct elements. But now we might wonder that over time, since the algorithm is randomized, it is conceivable that the adversary might learn something about the internal randomness of the algorithm. And if it can learn that, then potentially it can make the algorithm fail with high probability. So to summarize, in this model, the adversary's future queries may depend on the entire transcript of previous queries and responses of the algorithm. This is actually a very natural setting in real-world applications. For example, if I'm querying a database, it's very likely that my next query will depend on my previous queries and my previous answers that I received. Also, many optimization procedures use sketches as subroutines, and future updates usually depend on previous updates. But there is a concern that over time, by interacting with the algorithm, the adversary might learn a lot of information about the internal randomness used by the algorithm. And importantly, all previous techniques required that input stream is independent of the internal randomness of the algorithm. Over the last few years, there have been many works focused on designing streaming algorithms that are adversarially robust. For example, this first paper provided 2 techniques, one of which is sketch switching, which essentially initializes many independent copies of sketches with fresh randomness, and then Over time, when it feels that the algorithm learns a lot of information about one of the sketch's internal randomness, then the algorithm will just switch the sketch that it uses to answer queries. So intuitively, the goal here is to conceal the internal randomness from the algorithm. Similarly, there was a technique that used differential privacy to protect the internal randomness of the algorithm. And overall, this line of work has already provided nearly tight results for adversarial robustness in the insertion-only case. More generally, a stream can contain insertions or deletions, though. And here, each update will be represented by at comma delta t, where at is the coordinate of the frequency vector that is being updated, and delta t is the amount by which we increase or decrease that coordinate of the frequency vector. For simplicity, we can assume that delta t is plus or minus 1, where it corresponds to either deleting one copy of an element or adding one element to the stream. And in the robust setting, each such insertion or deletion can be chosen adversarially and may depend on the entire sequence of updates and answers by the algorithm. Currently, the best known adversarially robust algorithm for distinct element estimation uses roughly m to the 1/3 space, and in particular, no sublinear algorithms are known. Moreover, we don't even have algorithms that get a constant factor approximation in space poly n. So the last component we will need before we can state our main result will be a linear sketch. A linear sketch is an algorithm that first samples a random matrix A and then maintains A times X for the frequency vector X throughout the stream. And finally, when the algorithm needs to provide a response or an estimate, it will compute f of AX, where f is some estimator. In fact, previous works have shown that all insertion deletion streaming algorithms on a sufficiently long stream might as well be linear sketches. So this is a very strong statement, and it depends on some important caveats. For example, the sufficiently long stream here will have to be doubly exponential. But nevertheless, this is a very important result that shows the generality and prevalence of linear sketches. And indeed, all known sketches for insertion deletion streams are linear. Okay, so now we're ready to say our main contribution. We show that there is a constant epsilon, so that any linear sketch which uses r less than n to the c rows and gives a 1 plus epsilon approximation to the L0 on an adversarial insertion deletion stream can be broken using just r to the 8th queries. So actually, this is an exponential improvement over the previous known length of an attack against an L0 sketch. Next, we'll talk about the intuition for this attack. And to do that, we'll need to define one more thing, which is the promise problem against which we designed the attack. This will be the gap L0 norm problem. Let's fix some parameters alpha and beta. And the goal will be to distinguish between the case where the L0 of x is less than alpha n or bigger than beta n. And the algorithm can answer arbitrarily if neither of these cases holds. Importantly, any multiplicative 1 plus epsilon approximation algorithm for L0 can also solve the gap problem for sufficiently small epsilon. Now, we'll try to give some motivation for this attack. Let's think about how the linear sketch will work. The sketch will sample some sketching matrix A, and then for any query X, it will observe the output of AX. Intuitively, the output of this matrix vector product will reveal a lot of information on certain coordinates of X and very little information about other coordinates. We will say a coordinate of an input vector is significant if the sketch learns a lot of information about it. So right now, the definition of significant is very vague, but over the next few slides, we will try to formalize what we mean by a coordinate being significant. Let's look at this example. So here, the sketching matrix is given here, and the input vector is here. The sketch will compute the product AX, and notice that if we look at the first row, which is 0 in all coordinates except for 1 in the fourth coordinate. When I multiply this row by the input vector, I will exactly retrieve the value of x4. So clearly here, the fourth coordinate of the input vector is very significant to the sketching matrix. Meanwhile, when I multiply the second row by the input vector, it does not seem to capture very much information about any particular coordinate. So let's think why this discussion is important. Well, overall, the adversary will try to gradually learn the sketching matrix. And the strategy will be as follows. We will try to iteratively identify the significant coordinates and set them to 0 in all future queries. To see why this is a good idea, let's think about one round. If I found one significant coordinate and made it 0 in all future rounds, the algorithm can no longer use this coordinate to come up with the answer for the approximate L0 anymore. After we eliminate many coordinates like this, it will be harder and harder for the algorithm to answer correctly. And finally, once we potentially learn all our significant coordinates and make them 0, while others might not be 0, the sketch will think that the L0 is very small, while it might not be. It might just not observe very much information about the other coordinates. So once we have learned all significant coordinates, the query algorithm will have to necessarily rely on the other coordinates, which were insignificant, and the sketch did not learn very much information about. Intuitively, since it does not have very much information about those coordinates, the sketch will likely fail with high probability at this point. Now let's focus on an important extreme case. Suppose the sketching matrix A samples a subset S of R coordinates of X. We can think of A as having R standard basis vectors as rows, so it will exactly see the values X sub I1 through X sub IR. And as I said earlier, the attack will be to identify the significant set of coordinates S, and then place zeros in S and non-zeros everywhere else. In the next slide, I'll try to explain how we can find this set S in the extreme case that the matrix looks like this. So for this part, we will actually import an important result from the literature on interactive fingerprinting codes. So before I say the result, I'll define the interactive fingerprinting code problem. Here, an algorithm P selects a secret set S of little n coordinates, which is unknown to the fingerprinting code. And over time, the fingerprinting code F will try to identify the secret set S by making adaptive queries CT. For each query CT, the algorithm P must answer consistently with some coordinate in CT. This means that it needs to return an answer which is equal to some Ci of T for some coordinate I in N. But an important restriction is that the algorithm can only observe the value CIT for coordinates I that are in the secret set S. So the algorithm will need to distinguish between inputs that are all zeros or all 1, but it can only observe the values CIT for I that's in the secret set S. So a previous result on this showed that there exists an interactive fingerprinting code with length roughly n squared, where n is the size of the secret set. Now, the gap L0 norm problem, which we hope to find an attack against, needs to distinguish between the L0 being at most alpha n or at least beta n. So in fact, this is a stronger requirement than the one for the algorithm in the fingerprinting code, which just needed to distinguish between all zeros and all ones. So in fact, there is hope that we can use a similar attack as they provide in this previous work against our problem for gap L0 norm. And this is indeed what we do. So now let's continue to develop our definition on what is a significant coordinate. So far, we know that I is significant if there is a standard basis vector EI as a row of A, but there might be other cases that a coordinate is significant. Let's look at this example. Here we have a second row with a very, very large value in the second coordinate. And in fact, when I multiply this row by the input vector, this 999 will make the weight of the second coordinate of the input vector very, very large, to the point that the sketch will learn a lot of information about the value of x2. So we should incorporate this type of example in our definition. So observe that since the algorithm has AX, it can also recover Y transpose AX for any vector Y. And our working definition will be if there exists Y such that the ith coordinate of Y transpose A squared is at least 1 over S of the total L2 norm of Y transpose A, then we'll say that coordinate I is significant. So this is actually corresponding to the leverage score of column I being very large. So far, we consider a coordinate to be significant if these two conditions are true. But let's look at one more example to try to formalize our definition. So in this case, if we look at the last coordinate of this row with this one matrix, which is a row, with the last coordinate being 3, 3 might seem like it's not a very heavy coordinate compared to the other ones. But if we look at the output of A1 times X mod 10, then we actually see that the sketch can exactly recover the value of X sub n. So we should somehow incorporate this into our definition of significance. In fact, if we look at the fractional parts of the values of this row, we'll see that the last value, 3/10, is very heavy. The fractional part is very heavy compared to the other fractional parts, which are 0. So this leads to our final definition of significance. We will say that I is significant if there exists Y such that the fractional part of coordinate I is much heavier than 1 over S times the total L2 norm of the fractional parts. Now, to summarize, this is our current set of observations about what makes a coordinate significant. And actually, we can observe that if a coordinate I satisfies condition 1 or 2, it will also satisfy condition 3. Finally, let's see how we can use this definition of significance in our attack. The algorithm has access to linear sketch AX, and let's see what will happen if we pre-process the matrix A into a larger matrix A prime that has more rows that separates the significant coordinates. What I mean by this is that I will add a standard basis vector EI for every significant coordinate I that I find. Now, if I add all of these rows EI, I can actually, without loss of generality, assume that the algorithm uses the matrix A prime, the preprocessed matrix A prime, instead of A, as A prime can only be stronger. Why is A prime stronger? Because if I add the standard basis vector EI, then it's almost like I'm making the sketch fully observe the value of xi. So this, when it previously might have only partially observed it, now I will make sure that the sketch absolutely knows the value of xi. So this only makes the sketch stronger. Now, for each, more precisely, what I will do is for each row that has a significant coordinate, as I see here, I will replace this row by 2 rows. I will add the standard basis vector corresponding to the significant coordinate, which we have here. And then I will zero out all of the other rows in this coordinate so that the set of ones is completely disjoint. As a result, I will get a matrix A prime, which is a combination of a sparse part, S, and a dense part, D. And the sparse part will consist of standard basis vector rows, which correspond to the significant coordinates that we found. And the dense part will have no significant coordinates. As we see here. Now, as part of our argument, we show that this preprocessing only adds of R times S times log n rows to create this new matrix A prime. And note that if there were no dense part, we could have just used the fingerprinting code right now to attack S and learn the set of significant coordinates. But since we do have a dense part, we will need to handle that. And to do that, we will try to show we will design a family of distributions such that if I sample from this family, then the dense part will not help the sketch to find the L0 of the input vector. So in particular, I design a family of distributions D over a bounded range of integers, such that for any distribution dp in this family, the probability of sampling x such that x is 0 is going to be p. And for any p and q in some range ab, the total variation distance between the dense part times x sub p and the dense part from x sub q will be very small. So here x sub p is sampled from dp and x sub q sampled from dq for some different parameters p and q. So here, the total variation distance between these two distributions, dxp and dxq, will be very small. And we show that these are the only distributions that we need in order to make the fingerprinting code attack work, so that the dense part does not help the sketch to distinguish between vectors with very different L0 norms. More concretely, if I sample x from dp, then the expectation of the L0 will be roughly pn. And if I sample x from dq, then the expectation will be roughly qn. So the expectations of the L0 norms are very different, but as we have in this second condition here, the marginal distribution of dp is nearly identical for x sampled from dp or from dq. So the algorithm will not be able to use the dense part to distinguish between these two cases, and will have to use the sparse part. However, as we said with the fingerprinting code attack, we will learn the sparse part and set the sparse part equal to 0. So over time, the algorithm will have to use the dense part, which, as we show here, will not be useful, and the sketch will ultimately fail with high probability. Overall, our attack proceeds by preprocessing the matrix A into a new matrix A prime, which is a combination of a sparse part and a dense part. And as I said earlier, this matrix A prime only makes the sketch stronger. Then we can attack and learn the sparse part S using the fingerprinting code. And we argue that we can find a distribution family such that the dense part D does not help the algorithm to distinguish between query vectors that have very different L0. So to summarize, our main result is an attack against L0 linear sketches for adaptive streams. And we show that any L0 sketch can be broken using R to the 8th queries. And we actually have two additional results in the paper, one of which uses a very similar format of attack against real-valued linear sketches with bounded subdeterminants using poly-R queries. And we also have an additional attack that uses a different format that is for linear sketches over FP and uses a smaller number of R to the 3rd queries. Finally, some future directions would be to either generalize our attack against linear sketches for L0 for general L0 streaming algorithms in insertion deletion streams. Or alternatively, it would be interesting to create attacks on linear sketches for LP estimation in adversarial insertion deletion streams. Thank you so much for listening.